Describing circular motion is more challenging than describing a linear motion. When an object moves from point A to point B in a straight line, the Cartesian coordinate system can be arranged in such a way that only one dimension is relevant. Thus, there's only one equation to solve. However, when the path is circular, tracking motion becomes more intricate. If a body moves from point A to point B along a circle, expressing its position using the Cartesian coordinate system requires the use of two coordinates simultaneously, resulting in two variables and two equations to solve. There's a method to simplify this complexity. Since the radius of the circle remains constant, utilizing the angle of rotation of the body's position vector, delta theta, offers much simpler mathematics for tracking circular motion since there's only one variable and one equation to solve. Nonetheless, certain motions combine circular and linear motion. Therefore, it's essential to ensure a smooth transition from linear to circular motion and vice versa. To calculate the distance traveled, delta d, the simplest method is to multiply the radius r by the rotation angle delta theta. The distance traveled is directly proportional to these quantities. However, calculating the actual distance delta d using degrees as the unit for the rotation angle yields an inaccurate result. Therefore, a new unit of measurement for angles is necessary. The circumference of a circle represents the distance traveled by the object in one complete rotation, which is 2r pi. By substituting delta d with r times delta theta and cancelling r on both sides, delta theta for a complete rotation should equal 2 pi to achieve a numerically accurate result. This new unit of angle measurement is known as radian, abbreviated as rad. As the angle delta theta is the ratio of the distance traveled, delta d, to the radius r, when the distance covered is equal to the radius, the rotation angle is 1 radian. Now let's define and express the other quantities of circular motion in a similar manner. The linear velocity is defined as the ratio of the distance traveled, delta d, to the time interval, delta t. By substituting delta d from the previous equation, v equals r times delta theta over delta t. When an object moves in a circle, the linear velocity always aligns with the tangent, hence it's known as tangential velocity. The value of the expression delta theta over delta t indicates the rate at which the position vector r rotates, its angular velocity, omega. Therefore, the tangential velocity v can be represented as the radius multiplied by the angular velocity. Acceleration can also be described in terms suitable for circular motion. The acceleration being discussed is defined as the change in tangential velocity magnitude per unit of time, delta v over delta t. It aligns with the tangential velocity and is known as tangential acceleration. By substituting velocity from the previous equation, a equals delta r times omega over delta t. As the symbol delta represents a change in a quantity, and considering that the radius r remains constant in circular motion, delta does not affect radius, allowing us to place it directly before the angular velocity omega. The portion of this equation, delta omega over delta t, can be represented as alpha, angular acceleration, which indicates the rate of change of angular velocity. Consequently, tangential acceleration A can be expressed as the product of the circle's radius r and angular acceleration alpha. This approach enables us to represent all kinematic quantities of linear motion using the circle's radius and the corresponding circular motion kinematics quantity. Quantities used to describe circular motion are vectors, with the direction of the axis of rotation oriented by the right-hand rule, which states that when fingers indicate the direction of rotation around the circle, the thumb indicates the direction of the vectors of angular velocity and acceleration.